Welcome to Lecture 5.3, Evaluating Definite Integrals. What we're going to do now is we're going to put together all the concepts around integrals that we've just come through. We've looked at antiderivatives, which is another kind of way of saying the integral, that the integral is the antiderivative. We've looked at how to calculate those, or how to find the formulas for an integral, using some new formulas or kind of reversing what we did with derivatives. In the last section we understood that the area under a curve could be calculated by taking rectangles. Okay, and so now an interesting thing's going to happen is that we have a shortcut, and this is where the power of calculus and specifically the integral comes out. We can calculate the area under a curve using an integral. Okay. So in the last section we computed integrals as the area under the curve by using limits of Riemann sums. The Riemann sums are using those rectangles. But that can be a long and difficult process, especially if we have a more complicated formula. Sir Isaac Newton discovered a much simpler method for evaluating integrals, and this was followed a few years later by Gottfried Wilhelm Leibniz. Now this is a long-standing battle in calculus and math history about who discovered it first and who discovered what, and I don't even know if there's an answer to that. But obviously Leibniz should wear because he has bigger hair. Anyway, so they realized that they could calculate the integral, and you're familiar with this integral from f of x, the integral of f of x dx. Now what we've added to this are limits. So we're going to evaluate the integral from values of x equals a to x equals b. So this is just like we had here. So if this was our integral, we'd be evaluating the integral from 0 to 1. From 0 to 1. Okay? So this is evaluating the integral over an interval. Okay? So they realized they could calculate the integral over an area if they knew the antiderivative f of x. And remember, the integral of f of x is the antiderivative. And so this was called the evaluation theorem. Okay? So if f is a continuous function on the interval, closed interval ab, then the integral from a to b of f of x dx equals that antiderivative evaluated at b minus that antiderivative evaluated at x equals a. So we find the antiderivative, or the integral, first, the formula, then we plug in the upper limit, b, calculate that value, and subtract the calculated value of the lower limit. Okay? And remember, this is just saying that f is the antiderivative, or capital F is the integral of little f of x. Okay? So let's look at an example from the last section. Remember, we were evaluating, we were looking at the curve, I wish I'd drawn it here, of x squared from 0 to 1. And so let's try their formula. So remember, what we're going to do here is we're first going to take the integral of x squared dx. Well, this is a power rule, right? The antiderivative is 1 over n plus 1, 1 over the exponent plus 1, times the function to a new exponent of plus 1. So this is a very simple integral. We get 1/3 x cubed, right? Now we want to evaluate this from 0 to 1. Now notice when we have definite integrals, this is called a definite integral when we have limits on it, we no longer have a plus c here because we know exactly what we're evaluating it from. So we first put the upper limit in, 1, we plug that into the formula, and then subtract the function with the lower limit, or 0, in there. Okay, so we plug the 1 into the formula, so it's 1/3 times 1 cubed, x equals 1, so it's 1 cubed, minus 1/3 times x equals 0, so 1/3 0 cubed. And this just gives us 1/3. And if you remember, as we were calculating those, we were getting, remember the very first time we did it, it was between 2,6 and 4,6. And then when we saw as the number of rectangles went larger, it got closer and closer to 0.333. Okay, so this is the actual value, or the calculated value of that area. This is a reminder, we've seen these before. I'm not going to go through these, but I wanted to give these to you again. Your online text, and I may not have said this, hopefully I've said this in earlier videos, the back of your online text has a whole, I don't know if it's called an appendix or a reference section, and these might be good ideas for you to print out. They are like 1 page long. You can print from your online text, and it has like a whole set of formulas for integrals and derivative functions. Okay, you are responsible for these. Okay, you are responsible to know these. All right, let's try a couple of these. If you want to, hit pause and try them on your own, and then we can do them together. Excuse me. So this first one, we know the integral of e to the x is the same, just e to the x, so we're going to evaluate it from 1 to 3, which means we're going to plug in the value of 3 first, and then subtract the value of x equals 1 plugged in. And so we just get e to the cubed minus e. This is our answer here. We don't need to go into any decimal form. Okay, oops, sorry. So for example 2, it says find the area under the cosine curve from 0 to b. Okay, so here we're going to evaluate this first from 0 to b. Okay, and then it tells us that b goes from 0 to pi over 2. But let's first calculate this integral from 0 to b. So we get the integral of cosine, of course, is sine. So we're going to have the sine of b minus the sine of 0, but remember the sine of 0 is 0. So we get sine of b minus 0, which is just the sine of b. Okay. Now taking b equals pi over 2, the area under the cosine curve from 0 to pi over 2 is sine pi over 2, right? Because we can go from 0 to pi over 2. And we just get the area of 1. Okay. From 0 to pi over 2 is simply 1. Now we could have done this the same way. We could have put pi over 2 in there. But since we're going from here to here, 0 to pi over 2, we just needed to put the value of b in there, okay? Because we can see that we could have done it the other way around too, if we had put those values in, but we're getting the same values, pi over 2 minus sine 0. All right. So this is really key, and I want you to pay close attention to this, okay? Because this is where a lot of students make mistakes because they're not sure which is which, okay? So these are very simple concepts, and if you get this, this will help you in solving problems. So an indefinite integral is an integral that has no limits on it or no numbers on the integral sign. A definite integral has values on the integral sign, okay? Indefinite, no values. Definite, values. Okay, so again, no limits or values. Definite, limits or values. These are called the limits because we're going from the limit as x goes to b, or x goes to a from x goes to b. Okay, for an indefinite integral, your result is a function, or we say a family of functions, remember, because we add that c in there that we've gone through before. So here on an indefinite integral, you are going to get a formula or function. You're going to get some kind of equation with a variable. On a definite integral, you're going to get a number or a value. So let's look at this. Let's use the same formula. So if we take the indefinite integral of x squared dx, we get 1/3 x cubed plus c. This is the answer to the indefinite integral. If we take the indefinite integral from 0 to 1 of x squared, we get the indefinite integral, but then we evaluate it from 1 to 0 and get 1/3, and this is the answer. Okay, this is a key concept difference, understanding kind of the vocabulary and the difference. An indefinite integral, you get a formula or function. Do not forget the c. On a definite integral, you get a value. All right, so try these two problems. Again, hit pause. And then try them and then hit play again. So for example 3, notice we can separate this out and we get 10 times the integral of x to the 4th, pretty simple, minus 2 times the integral of secant squared x. Using our power rule and then what we know from our antiderivatives, the first integral becomes x to the 5th over 5 with the power rule, and the integral of secant squared is just tangent. So here's our, well, let's clean it up a little bit more. We need to get rid of that 10 and 5, we need to simplify that. And so our answer here is 2x to the fifth minus 2 tangent x plus c. Okay? I think we've already covered this, but I don't add a c here and then add a c here and then have two c's, etc. Since c is a constant, we can just, since we have a one string of equations, we can always just add a c at the end because it's a constant. So that even if the constant here was 1 and the constant here was 2, you know, then this c might be 1 minus 2 is negative 1. So it doesn't matter because it's still going to be a constant. Okay, so we don't add more than one c here. We do some when we're trying to solve for them, and we'll see that later. Okay, again here we can separate this. This is two power rules, but now we're trying to evaluate from 0 to 3. The integral of the first is x4 over 4 minus 6x squared over 2, evaluated from 0 to 3. I should have simplified this first, sorry. So this is obviously 3x squared, and this is 1/4 x to the fourth. So we plug in 3 to both of these first, so we get 1/4, 3 to the fourth, minus 3, this is 3x squared, remember, 3 times 3 squared, that's in the first. Always be careful when you have subtractions, use a lot of parentheses because it's easy to mess up. So then I put 0 in, 0 to the fourth over 4, minus 3, 0 squared, 3x squared, this again, remember this is 3, I should have simplified that. And so I do this piece here, so I get 81/4 minus 27. I would have done the parentheses first. Here they've just dropped the parentheses, so it's minus this, minus a minus then becomes plus. And so I end up with negative 6.75. Again, whenever you have subtraction in a problem, slow the hell down. Use lots of parentheses. This is where we all make mistakes in life with negatives. Okay. So here's an example of a what looks like a really complicated formula. It's often good to see if you can simplify the integrand first, and this one's quite easy to simplify. Notice that if we divide, since there's only one term in the denominator, if we divide each term in the numerator by that t squared, we get a much simpler formula. Right? 2t squared over t squared gives us 2. T squared times the square root of t over t squared gives us the square root of t, or t to the 1/2, minus 1 over t squared, or minus t to the negative 2. So now we have a simple power rule, we have a constant rule, etc. So this is a much easier derivative to find, or excuse me, antiderivative to find. The integral of 2 is 2t. The integral of t to the 1/2 is t to the 3/2 over 3/2. The integral of t to the negative 2 is negative t to the negative 1 over, it's not negative, it's negative because of the minus, t to the negative 1 over negative 1. Simplifying this, we get 2t plus 2/3 t to the 3/2 plus 1 over t. If I was going to solve this, I might write this 3/2 in terms of a radical because it's easier for me to solve, but you can also put it in your calculator with an exponent. So 2 times 9 is 18. The square root of 9, right, because this is the square root of 9 cubed, or so the square root of 9 is 3. 3 cubed is 27. 27 divided by 3 is 9. Times 2 is then 18. And if you take this, I'm not going to go through this. This is arithmetic, but in algebra, you should be able to do this. And then 1 over 9 is here. Put 1 in. 2 times 1 is 2. Again, notice here we're subtracting all of these. So they didn't use parentheses, which I would have done first. I would have done this whole piece here first in parentheses. So minus 2t minus, because it's really minus all of this, minus a positive is negative, minus another positive is also negative. This is where students screw up. They go, oh, it's plus, and they put plus here without the parentheses. And so the value gets wrong. Be careful with subtraction. And remember, all definite integrals are subtraction. The upper value minus the lower value. So use parentheses here and be very careful. Again, the square root of 1 is 1. 1 cubed is 1 times 2/3. And then 1 over 1 is 1. And then you do the math and you get 32 and 4/9. Okay, let's just do a little reminder here. A derivative is a rate of change. Okay, we knew that. And the derivative is specifically the instantaneous rate of change. Okay, an integral is also an antiderivative. That's how we first started finding them. So the integral of a rate of change is the net change, or simply the accumulated change. Okay, it's the accumulated change. So while a derivative was how things are changing in an instant, the integral tells you how much change occurred totally. Okay, so for example, we did some examples with, let's say, marginal revenue, right? How is the revenue changing with the next piece? So if we took the integral of marginal revenue, what we would get is the total revenue, which we already did a problem like that. And if we did it between, let's say, 1 and 5 years, we'd get the total revenue over 5 years. So an integral is your accumulated change. How much stuff is accumulated all together? If you're doing a rate of change, which is speed, then what your integral is going to give you is how far you've gone, because speed is position over time, where you are over time. It's how your position is changing over time. And so if you did the integral of that, what you would get then is how far you've driven or gone. Okay? So the integral of a rate of change is the net change. And this is just kind of giving you a concept. So if V represents the volume of water in a reservoir at time t, right? So how much water is in the reservoir at time t, then its derivative, V prime t, is the rate at which the water flows into the reservoir at a specific time, right? So this is how fast the water's going in. So if we took the integral between two time periods of the derivative, we would get how much water is in there at the end minus how much water it began with. And so this tells us how much water went into the reservoir between these two times. It gives us the accumulated change in the volume. Okay? So let's look at a problem and see if we can sort this out. And this is a little bit of a tricky problem, but I put it in here on purpose because I want you to think about this, because you have to be thinking conceptually when you're doing problems as well. All right. Since velocity is the rate of change of distance, and it's really not the rate of change of distance as much as position, and so this is a little bit, then the integral of velocity will give us the position or distance. Now, position and distance are a little bit, they're different concepts, and so I want to be clear about that. And that's where this problem gets a little bit tricky, and this is one of the reasons why I wanted to do it. Okay, so if I'm leaving Dallas, and I drive 60 miles an hour for 1 hour, then, and let's say I'm driving towards Austin, then my position may be that I'm now in Hillsboro or something, but my distance is the 60, okay? So my position is often a relative thing. It's relative. You might think of it like a timeline, okay? So, so I start in Dallas. Let's say I drove 60 miles to Hillsboro, and then I drove 30 miles back to some suburb, let's say Cedar Hill. I don't know if any of these are right in Dallas. So I drove 60 miles back, and then I drove 60 miles out and then 30 miles back. Well, my position now is only 30 miles south of Dallas. My position is only 30 miles south of Dallas, but while the distance I drove was 90 miles. So position is like a number line thing. It's relative to 0 or relative to your starting point, where distance is the total you've driven. And that's really key in this problem, and you'll see. Okay? So the first thing says find the displacement of the particle during the time period. Where is the particle now? So a particle moves along a line. Its velocity is here. Its velocity is given as t squared minus t minus 6. So find out where the particle is now. Okay, so its position at 4 minus its position at 1, because we're looking at the displacement between 1 and 4. So between 1 and 4, where did the particle go and end up? Okay, displacement is the integral of velocity. Okay, So we take the integral of velocity from 1 to 4. This is a very simple derivative. The integral from t squared, very simple integral. The integral from 1 to 4 of t squared minus t minus 6, the formula given in the problem. We have the integral. These are very easy pieces. T cubed over 3, t squared over 2, and minus 6t. These are each of the pieces of the antiderivative. Evaluated from 4 to 1. Plug in 4, calculate. Plug in 1, calculate, and then subtract those values. And you get negative 9/2. Okay? So the particle, because remember this is in meters per second, so the distance or the displacement is going to be in meters. The particle is 4.5 meters to the left of its starting position. We know it's to the left. Think of a numbered line because I'm going in the negative direction. So the particle is 4.5 meters to the left of its starting position. Okay? Now, in order to figure out B, we have to really think through the problem. Does the car or does this particle move in a negative direction as well, like the example I gave in the beginning? If I drive 60 miles out and 30 miles back, I end up 30 miles from where I started, but my total distance is actually 90, because you got to remember that distance is an absolute value. For example, if you drove to Austin for a party on Friday and came home on Sunday, you ended up back at the same place, but you wouldn't say, so your displacement is 0, but you wouldn't say you drove 0 miles, right? You'd say you drove 300, let's say 150 out and 150 back. And so that's what this concept is about. So if we look at this, notice that we get t squared minus t minus 6, which we can factor here. So we can look and find the x-intercepts, right? So we have an x-intercept of -2 and an x-intercept of 3. Okay, well the -2 doesn't matter because we're not going to it's not in our interval here between 1 and 4. But when the other x-intercept is 3, so we know when x is less than 3, we have a negative value, right? If x is 1, if x is 2, etc. So all the values up to 3 are negative or 0. When it gets bigger than 3, then the value here is positive. So here what we have to do is we have to actually separate this into two integrals. We're going to separate the whole interval between 1 and 3 when it's negative, and we're actually going to take the integral of the negative because a negative of a negative will give us a positive value. And then we're going to add the last piece from 3 to 4 where the velocity or the displacement is actually positive. We're going in the positive direction. Okay? So you have to be mindful here when you're dealing with these distance problems or any absolute value problems. If the formula comes out to a negative value, you're going to take the integral of the negative of the formula. This is not very hard to do, so all we do is multiply the formula by -1 and we get this for the first piece. We've already done the second piece, we just plug it in, and then we just do these separate pieces here. And I'm not going to walk through these, you can do them yourself, but see if you get that value. Alright? So it's very important you pay attention to concept, especially when the concepts of absolute value or distance